Okay. Any questions? No? No questions? Delight. What do we talk about today? Pressure changes. Huh? Come on. We talk about pressure changes. Very important topic. If I give you more information, today's lecture will be in the exam. Okay? My appreciation for your attendance will be. Yes? Pressure changes. Pressure changes, pump, compressor, turbine, valve, pipeline system, those are pressure changes. Now, think of pump, calculate either the power requirement or the power produced, and try to know the terminology. Fluid power, the amount of power delivered to the fluid power. Brake power or shaft power, amount of power required for the pump. Brake power or shaft power. So shaft power is equal to fluid power divided by pump efficiency. How about net positive suction head? What is the definition of net positive suction head? Natalie, avoid my eyes. What?
That's like the distance that goes.
Billy, avoid my eyes, I ask.
Can you repeat the question?
Well, my question is, what's the definition of net positive suction head? What is the net positive suction head? You learned in fluid mechanics. You don't remember? No? You didn't learn fluid mechanics from me? What is good?
Isn't it the height that it goes that a pump would push water up or something like that?
That's called head. That's called head. Head is how much pump can pump.
How much pump can pump water up?
How about net positive suction is a different thing. I am looking for one word. Huh?
Capacity.
Capacity. Oh. Net positive suction head is the amount of head required to avoid cavitation. That was what I was looking for. Cavitation. Yes. Amount of head required to avoid cavitation in the suction side of the pump. Suction side. We have suction side, discharge side, suction line, discharge line. You remember? Anyway, net positive suction head is the amount of head required to avoid cavitation in the suction side of the pump. Please look at fluid mechanics or just Google. You find out. We will look at pressure changes. Let's look at pump first. Very simple operation. As you can see, we have pump. We try to pump water. Yes, and then input specification, output pressure is given. Pump efficiency, drive efficiency is given. Okay. Where do we use pump? Imagine CDO Fairfield water supply system. We are focusing CDO Fairfield, Fairfield CD water supply system. We have four different the pipe design in this case. We are pumping water. We are designing four different piping systems of CDO Fairfield water supply system. What four different piping system? We use 1 inch schedule 40 pipe, 3 inch schedule 40, 1 inch schedule 80, 3 inch schedule 80. So 1 inch, 3 inch, those are nominal size. Usually when we say 1 inch, 3 inch inside the diameter, pipe inside the diameter, it's not exactly 1 inch or 3 inch, but we call it nominal size. Nominal means industrial standard size, 1 inch, 3 inch. What's the difference between schedule 40 and schedule 80.
Wall thickness.
Wall thickness. Eh? Look, can you explain more clearly?
Schedule 80 is thicker pipe.
Wonderfully. So you increase the schedule number, is wall thickness increases. So schedule 80, the wall thickness is thicker than schedule 40. If I talk about 1 inch schedule 40, 1 inch schedule 80, then the inside diameter, okay, is different. Even though we say 1 inch, so if I explain a little bit clearly, so that you can have some idea. Okay, we have a piping system, so we have pipe here. Even though I say this one is 1 inch, schedule 40, what's going on? And this is 1 inch, schedule 80. The outside diameter is the same. Outside diameter, this is the same. And as you can see, this inside diameter is different. So the schedule 80 has a thicker wall. Looks as wall thickness is different. Schedule 80 has thicker wall. When do you use thicker wall? Even though the inside diameter is smaller, when you deal with high pressure fluid, when you deal with corrosive chemicals, we need a thick wall thickness, thicker wall, high chemical. So that's different. What's going on? Come on. In this case, we are designing 4 different piping systems, water supply piping system. Okay? So let's try to design and simulate what we are in. So I will use specialty chemical symmetrically. So I'm going to design pump and 4 different piping systems. We only use water, one component. If you go method, we are dealing with only water. You can method assistant. If you see water only, we are using water only, And as you can see, STEAM TA is ASME 1967 STEAM table, STEAM MBS 1984, IAPWS, International Association for Standard of Water and Steam. And this is, so we can use any STEAM table, but the method assistant recommend IAPWS 95. You can choose anything here, but or STEAM table or STEAM MBS or IAP WS 95. Yes, we only have one component. So if we learn the simulation, we get some warning. It says binary parameters are missing. Oh, we have only one component. So we will absolutely have the warning, which we can ignore. Yeah. Let's go next simulation window. If you look at model palette, we are looking at pressure changes, the pressure changers. We have 6 different models: pump, compressor, turbine, multi-stage compressor, valve, pipeline. Let's look at it pump. Okay? And we have input stream, pump, output stream. Very simple. I'll say pump. Okay? And information, all information is given. 25 degrees Celsius, 1 atm. Water is pumped to 10,000 kilogram per hour. Next, we are working on pump block. So if you look at here, this is a pump unit block. We can do pump or turbine. Discharge pressure is given, so I click discharge pressure. 15 ATM, and pump efficiency is given 60%, 0.6. Drive efficiency 90%, 0.9. If you leave it empty, those efficiency, Aspen will take 100%. So if efficiency is given, you can put. If it's not given, Aspen will take 100%. 1. Now, whenever you use pressure changers, always pay attention to check flashing options. So go to flashing options and then check valid phases. In our case, valid phase liquid only. We are dealing with water. Okay, I am happy with that. So liquid only. Everything is fine. Then run the simulation. Make sure no errors. We will have one warning that says binary parameters are missing because we are missing only one component. That's okay, acceptable. So we have no error. Then we can check our result. So if you go pump, you can check the result. What we are interested in here, as I said, fluid power, brake power, or shaft power. And then electricity or net work required is 7.3 kilowatt, and shaft power power required for the pump is about 6.6 kilowatt because of that the most of drive efficiency, and from the pump efficiency 60%, so the fluid power delivered to the fluid is about 3.95 kilowatt. Anyway, by design pump, important information here, net work required. Okay, net work required about 7.3. Okay, pump was easy. Let's try to install 4 piping system and see the effect water supply system. So we have 4 different pipe systems. I will install 4 piping system. Little pay attention from now. Alright, I can use manipulator because this duplicate will replicate our input system much easier. So I use one duplicate, and then I will connect input output for the piping system. Okay, I'll name it P1, P2, P3, P4. And let's name it just P1 input, P2 input, P3 input, P4 input. This is duplicate. P1 out, P2 out, P3 out, P4 out. Okay? Now, what's the difference here? As I said, the first piping is 1 inch schedule, 4 in. Let's make it larger so that you can see where. How about next pipe? Anyone? 3 inch schedule for it. Thank you. How about next one? 1 inch schedule 80. How about next? Wonderful. 3 inch schedule 80. We are designing 4 different piping systems. So you can imagine 1 inch and 3 inch piping size, the different scheduling. Yes. Let's go next. Don't know what to do next. Now we are working on P1 pipe unit plugin. We are running new. pressure changers, pump to turbine compressor, valve pipe pipeline pressure changers. If you look at our slide, length is given 30 meter, and we know, okay, pipe schedule. So I can choose to use pipe schedules. Material, there are two different materials, carbon steel or stainless steel. We are dealing with water, so carbon steel is cheaper. Carbon steel is perfectly okay for water. Carbon steel. Schedule 40 and nominal diameter 1 inch. Schedule 40. We are dealing with pressure changes. I told you to check one thing. Whenever you are dealing with pressure changes, Joe was looking at me, so flash options. Check the valid phases. So you go flash option. Right now it's vapor liquid. Can you pump vapor? No. That's why we try to avoid chemication. So we don't pump vapor. You choose liquid only. Water. Yes. We are working on type 2. Same. Length is 30 meter. We know pipe schedule. So schedule, second one is schedule 40, 3 inch. Schedule 40. And then check flash options. Valid phases, liquid only. Same thing I can do quickly now. The third one is 1 inch schedule 80. Valid phases, liquid only. Fourth one, same as 30 meter. We are designing for 30 meter lengths. Carbon steel, schedule 80. 3 inch schedule 80. Flash options, liquid only. Let's try to learn the simulation. Okay, we got no errors. One warning. Okay. Binary parameters are missing. So if I check my pressure profile, can I use 1 decimal point? So over here, I can check 1. So we can see in 1 decimal point. If we use 3 inch schedule 40 or 80, as you can see, we do not have any pressure dropping, right? So measuring pressure drop is very important in industry, especially for pumping and piping system. Why? Lucia, you're nodding heads. Why?
It's gonna reduce the efficiency of the pump.
Reduce the efficiency, or we can design what kind of pump size is required for this system. So that's why pressure drop is very important factor. So if you look at here, if we use 1 inch, okay, 1 inch schedule 40, we got about 3.3 ATM pressure drop. If we use 1 inch schedule 80, we got about 5.3 ATM pressure drop. Jack, what's going on? Why? Huh? I couldn't hear.
What was the question?
Oh, that's the question. Oh, okay, let's go this side. Chase.
What's the question?
Okay. Can I deny on you? No? So, okay, let's look at it again. Or let's look at 1 inch schedule 40, 1 inch schedule 80. So, pipe 1, pipe 3. We are looking at, because 3 inch schedule 40, 3 inch schedule 80, there's no pressure drop, as you can see. So, we are looking at pipe 1, pipe 3. 1 inch schedule 40, 1 inch schedule 80. And if you look at the pressure drop, 1 inch schedule 40 got about 3.3 ATM pressure dropping. 1 inch schedule 80, we got about 5.3 ATM pressure drop. What's going on? Why?
Storm hole.
You I didn't ask me the question. Jared!
Yeah, since it's schedule 80, the interior diameter is smaller.
Wonderfully. And as I said, schedule 80, inside diameter is smaller than schedule 40. We are pumping 10,000 kilograms per hour of water. If you use schedule 80, because inside diameter is smaller, okay, to pump 10,000 kilograms per hour water, we will experience about 5.3 atm pressure drop. When you design piping system, you design like that, high pressure drop is not that good design. Why not just use the 3-inch schedule 40 or 80 for this system? That's what we are looking at. Yes? Now, if I increase this piping length, for example, for single family water supply, how long we supply water might be even 5 miles, 10 miles. So let's try to increase the distance. Maybe can we try 100 meters? Let's try first for every piping system. So the question is, can we use to design 100-meter length of piping for water supply? Can we use 1-inch schedule 40, 1-inch schedule 80, 3-inch schedule 40, 3-inch schedule 80? So if you look at here, we got one error, means something is not working. If you check here, which piping system is not working? Page, Brian, who can see?
1-inch schedule 80 is not.
1-inch schedule 80 not working, right? So as you can see, if you look at 1-inch schedule 40, pressure drop is already 11 atm. If you use 1-inch schedule 80, this system is not working. So for piping 3 system, if you are design using 1-inch schedule 80 or even 100-meter length, it's not going to work. Yes, you get idea, right? But even for 100 meter, if you use a 3-inch schedule 40 or 80, you can see the pressure drop is very small, trivial amount. Maybe if you are design more than 100 meter length of piping system for water supply, then you have to use 3-inch schedule. Make sense? Can we make this pipe 3? Maybe I can choose like 70 meter, let's try. Whether it works. It may work, but you will experience a huge amount of pressure drop. Maybe so. It's like 12.3 atm pressure drop is not that good design. So please play around. Okay? Not that difficult. But now the question starting. So far we just warmed up. Yes. Problem solving using optimization function available in Aspen. We exactly have the same pumping system and piping system. Now we know if you want to design longer distance, we have to use a 3-inch. So let's look at 3-inch schedule 40 pipe, but the length is 2,000 meters. Okay. Make sense? All right. The information for this system, we want to supply water, 10,000 kilograms per hour of water. We want to deliver or supply 2,000 meter length with a 3-inch schedule 40 pipe. The given information is, for this piping system, the annual total cost is given by this equation. So pump and piping, this system, annual total cost is given by this equation, and this first term is installation cost. We have to install pump and pipe. So the first term is installation cost. This second term is operational cost. Installation cost plus operational cost, total annual cost. Yeah? And this total annual cost, how do we estimate? We developed this equation. So we estimate by the equation total annual cost of this water supply system. D in this case is inside the diameter pipe, L is pipe length, K is roughness parameter. Roughness parameter K, you remember fluid mechanics, chapter 5, figure 5.10, roughness parameter. Yeah? penetration factor. In this case, K is Laplace parameter. And M is water flow rate. Unit of kilogram per second. So let me pay attention to those two units. Okay? Diameter is in meter, length is meter, Laplace parameter is meter, water supply flow rate is kilogram per second, and density, water density, kilogram per cubic meter. Okay, we know the equation, we know the unit, we know every definition of those variables. The question is, find out the optimal inside diameter of the pipe by performing optimization analysis in Aspen Plus. That's the question. Find out the optimal inside diameter of the pipe. At what condition? My question is to find out the optimal inside diameter of the pipe. At what condition or at what constraint can we find the optimal inside diameter of the pipe using the equation? Chase?
The lowest annual total cost.
Lowest annual total cost. Smart. Why? The equation is estimating annual total cost. We are looking for what is the optimal inside diameter of the pipe. Minimum annual cost. We find out this one D at minimum annual total cost. Make sense? Let's try to solve this question in Aspen. Let's solve the question. So please look at this information and this information. We will use the information. It says use optimization analysis available in Aspen to solve the question. So let me delete all of this. Okay, we are working on pressure changers. I will install pipe, and we have simple. I'll name it pipe. I'll name it this one as 3. Okay. Right now the pump is over, but we can do piping. So let's continue. In this case, what is given is 2,000 meter. So 2,000 meter. Pipe schedules are given, same as carbon steel. Schedule 40 and 3-inch diameter. And flash option, liquid only. I will reset. The question is, use optimization. We are learning new thing today. So if you go navigation pane, model analysis tool, there is called optimization below sensitivity. Very similar to sensitivity. So let's go optimization. If you look at here, there are 3 tabs we have to take care of it. Define, objective and constraint, and vary. Look up. What do you think we can vary? Joe, I think Joe knows. Huh? Pipe diameter. That's what we need to vary. Why? We are looking for pipe, the optimal pipe diameter. So we vary. Okay, we are going to vary pipe diameter. Oh, we know it. Now, what can we then define here? What do we have to define? Jason.
That equation.
Equation. What? We have to define the equation. Yes, the equation is given. We are looking for optimal diameter. We are looking at the equation. We have to define the equation. Now, there's for objective and constraint. What can we set objective and constraint? Constraint. As I said, at what constraint we are looking for optimal inside diameter. Weston. Who said it? Somebody said, Lillian?
The lowest annual total.
No, lowest annual total cost. Wonderful. So, logically, we developed the logic in Page. Yes? Okay, we developed the logic. We know, we have to define equation. Objective and constraint, lowest annual total cost. Vary, we vary inside diameter. Okay, let's go. Then as long as you develop logic, it's easy. Define, we have to define the equation. In equation, we have some variables. So let's define diameter first thing. Okay? Diameter is a piping. Pipe is unit block. So block variable. Pipe, unit block as I said. We are looking for inside diameter. So inside diameter in meter. That's the inside diameter. We have a length, pipe length. You can name the variable name as you wish. I just name myself like that. Okay? Pipe length. This is also unit block, pipe block. So I go block variable, pipe. And then we are talking about pipe length. So where's length? L. Length in meter. Oh, I'm happy with that. Next is roughness parameter. So I name it roughness K, roughness parameter K. Okay, roughness parameter block variable. Yes. Block variable. Type. Roughness. Do we have roughness here? Yes. Roughness in meter. Okay. So far so good. Next variable is what? Called M. So I can name it H2O mass flow maybe. H2O mass flow is a stream variable. So I choose a stream. Mass flow, not mass pressure. It's mass flow. Yes. Stream, input stream to pipe is S2. Component is water flow. Unit is given. So pay attention here, unit, kilogram per second. So just use the unit, given unit. Okay, now next we have to define density. So let's try to define density. I'll just name it density. Okay, density stream variable. Density is a stream property. So I can choose stream property. Stream maybe S2 input stream to the pipe. Property we are looking for density. But as you can see, we cannot find the density. If we cannot find the density, what do we need to do? Neil.
Yes.
Yes. Oh, Lucia didn't like it. Lucia didn't like it. You said yes.
I think there's a way for you to like define like add the variable yourself.
Exactly. When we did the liquid extraction, do you remember liquid extraction? We defined our own property on the property set folder because we are looking at different property or your own property. Just define. Where do we define? If you go navigation pane, there's a property set. You just define your own property. Can I define density? Now, we are looking at density. If you look at your densities for rho, RHO, density, unit is kilogram per cubic meter. Density of what? So when you define your own property, pay attention to these qualifiers. We are defining density of water. In liquid extraction, we define the mole concentration of MEK. You remember? Okay, so I define the density of water. Yeah? Let's go density. Now I can choose property set. Density is already available. Yes. Water fluid. We have water fluid. Whenever you look at it, fluid flow, water flow, gas flow, what is the most important parameter? What not important, but we always try to look at it. Okay, you have water flow or gas flow. We always try to look at one number or parameter. What parameter we are always trying to look at? Anyone? Yes, Canon.
Reynolds number?
Wonderful. Reynolds number. Can we define Reynolds number? Let's try to define Reynolds number. Why? Whenever you are dealing with fluid, liquid flow, gas flow, look at the Reynolds number. And then find out the flow pattern. Is that laminar flow? Is it turbulent flow? Is it transient flow? So maybe let's try to look at Reynolds number, even though in that equation we don't have Reynolds number, but we can look at it. Reynolds number. Reynolds number, Bloch variable. Okay? Bloch variable in the piping system. Can we see Reynolds number? Property, I think. Property Reynolds. Reynolds number. ID equals to 1. That's how we defined it. Next, objective and constraints. Clear up. According to our logic, what we need to put here, objective or constraint.
Minimize the cost.
Wonderful. Minimum cost. So we are looking for the minimum total annual cost. So we minimize and total cost. You can put maybe total variable, total cost. We want to try to minimize the annual total cost constraint. Okay? Now we know very. Delight, you were looking at me. When you look at me, means 딱히 많이 원하는 answer. I interpret that way. So Delight was looking at me. The question is, what do you beg? Wonderful. We beg inside. Why? We are looking for. We are finding out optimal inside diameter height. We have to vary that parameter variably. So we vary inside diameter, which is a Bloch variable, right? In the piping system, we are varying inside the diameter. In the meter, 0.01 meter upper, maybe 0.5 meter. So far, so good. We have equations. Jace was looking at me. Where? Huh?
I was going to see if you could go back to the objective constraints.
Objective and constraint, yes. Yep. Oh, but don't avoid my question with Jace. So far, so good. Where do you think we can define the equation? You are saying you're people. Fortran. So, if you look at this Fortran, we do simple math using Fortran. Yeah? So, Ryan, from column number, what we start executable statement? Column number. Column 1. No. Column 7. That's the fundamental knowledge you need to know. So if you didn't know, go back our slides available. Okay, there is a basic statement of Fortran. Executable statements start from column number 7. Very important. So we start from column number 7. Let's define our equation. So first term is installation cost. I will say first cost. first term cost, this installation cost is 229.8 times. Huh? Yes, Lucia.
Can you just explain again why we have to put it on column number 7? Like, how's it gonna change?
Oh, that's just the Fortran regulations.
That's just,
Yes, Fortran regulations.
So let's define what column one.
Column number 1, you can use C for comment. So you have to type C, and then you can put comment. Column number 2 to 6 is blank. You start from column number 7. Okay? Can you see? You can see? Can I make it larger? Little bit? Why not? So I define the equation. So first term cost is insulation cost. If you look at the slide, the equation is 229.8 times diameter. I named diameter is DIAM, diameter, and the exponential. You use 2 stars exponentially. So look at the Fortran basic statement. There is information in 1.072 times length. I said pipe length, PIP length. Yes.
You have two asterisks
For exponent.
for exponent?
Okay? Good. If you are not sure, make sure after lecture is over, I don't know what's going on. Please make sure if you don't know. It's nothing to be shameful. You don't make sure it's more shameful, even if you don't know. Right? Just make sure you know what you're getting. I am working on second equation. I will name it, divide the term as term. Then I define pipe length times water flow is named H2O, mass flow, power to the 3, divided by density, I named dense, I think, power to the 2. Third one, the second term is operating cost. So I named operating cost is equal to 168.71 times log is K divided by diameter power to be 0.25 divided by diameter power to be pips. Okay? Times I said term, the last term. And we are looking for total cost, which is F first term cost plus operating cost. We do simple math. Wherever we have equation, use Fortran. Let's try to get it. Oh my God, am I good or I'm lucky? You make some mistake, you will have like 1,000 errors. I got no errors. So when you have 1,000 errors, don't be frustrated. It's very normal. But might be from very simple mistake. Check like spelling. Sometimes H2O, somebody uses H2 But that mistake caused a headache. It took a long time to find out. It was all night long. No pain, no gain. No pain, no gain. Did I tell you? H2O, somebody uses H2 O and 0 is the same. Took a long time to figure it out, but that's the process. I got no warning error. Let's check optimization result. Optimization result. That's what we are looking at. What we are looking at optimal inside diameter of pipe. So according to that equation, according to our design, looks like about 6-inch piping is the best according to the total cost. We can minimize the total cost. Yes? And if you see all values are correct, the Reynolds number looks like initially when you use the 3-inch plus 51,000, if you use about little larger than 6-inch, it's about 25,000 Reynolds number. But the answer is this one. That's the final value. That's what we are looking for. Now we are looking for total cost. Where can we find out the total cost? If you go convergence, okay, for convergence, for solver, for result, if you look at here, objective function value is about $40,000. So the total value cost is about $40,000 for this system, pump and 2,000 meter piping using 6-inch schedule 40 pipe. Any questions? As I said, we are looking at pressure changes. Pump, turbine, compressor, valve, pipeline. Let's look at compressor and the turbine. Compressor converts electrical energy into mechanical energy. Turbine work will be done by the fluid to generate electricity. The turbine is to generate electricity. Now, if you look at here, let's look at quickly. We use turbine. We have three mixture of ethane, propane, and all information is given. So let's try to design. And then this one problem solving example, you just do by yourself, just for practice. But let's look at it so far here. We try to design turbine. So, can I install turbine here? Here's compressor and turbine. This one is turbine. So I want to install turbine. Let's try to install turbine. Now, this turbine uses hydrocarbons. So I have to define new hydrocarbons. Methane, ethane, propane. No timing. If you use hydrocarbons, you go Master system. Master system will recommend using equation of state-based property method. Peng-Robinson SRK. Now, initially we used the steam table. Now we have to use different methods in one flow sheet. Yes? Does anybody have idea? Quickly. No idea? Okay, I give you idea. Huh? You can sectionize. Choose here, right click, change section. You can create new section. So I sectionize the first simulation S1, second simulation S2. For change section, create the new section S2. We are using two different property methods. Go back to properties, okay? Go to method specification, flow sheet section, write down it, flow sheet section ID, S1, we use steam table, S2, we can use Peng-Robinson, different property method for different simulation in one flow sheet. Now if you come back simulation window, if you go flow sheet, okay, we have global and section 1, section 2. We are not using global, so global right click and delete globally. We use section 1, section 2. We can design and simulate two different designs in one main flow sheet. Now you go next. We are running out of time. You can try now. It's nothing special. And you just try from here. It will work. Let me make sure. Steve, Jacob. Showing you